Hey guys, I'm Tara Haydari, and this is Lab 4, where we're talking about oscillations. So the purpose of this lab is to create a computer model demonstrating the energy principle based on the analysis of the motion of a spring mass system. And a little bit of motivation behind this lab is that there are seemingly complicated motions, and we want to be able to understand and predict their future motions. And to do this, I'm going to walk through how to do this through this lab. So first of all, let's break it down. We want to discuss the contact forces and the distance forces acting on our spring, which is the system, and our spring mass system. And our agent, the spring, has a spring force, and our agent, the earth, which is a distant force, opposite of the contact force, and its force is the weight. And here are some fundamental principles that we're going to use in our lab, such as Newton's second law, Hooke's law, and really importantly, we're going to emphasize this energy principle. And I want to point out that the change in energy is going to be zero. So the oscillating spring mass system, I put it in tracker, and while examining the motion, I noticed a couple things. So first of all, we want to plug in the initial conditions and that we have here, and the T, which is the period of oscillation. If we manipulate the formula around a little bit, we can actually find the stiffness, and we find the period of oscillation by taking the average of the interval of periods, and then through that we found the stiffness, and then our F net is going to be equal to 0, so the static equilibrium observations are shown here to find the relaxed length, which is 0.903 meters. And here are just some manipulations in our glow script codes, just like we had to change the mass of the ball to 0.402 kilograms. We had to type in our initial vectors, and we had to type in some of the formulas, and we wanted to compute the like kinetic energy and all that good stuff for our results. So we manipulated a little bit of the formulas here, and this is just a continuation of the glow script code with a bunch of the fundamental principles shown here, such as Newton's second law or the momentum principle, and just some energy changes over here with potential energy and kinetic energy. And the results we found are shown here. The blue is the computational model and the red is the experimental. And here we see that there is some error, but not too much, and some what if and or but questions. Is the energy principle satisfied, and justify your answer. Yes, the energy principle is satisfied, because as the spring potential energy increases, the gravitational potential energy decreases, and vice versa, which makes the total energy 0. So the yellow line is the total energy, the blue line is the kinetic energy, the red line is the spring potential energy, and the green line is the gravitational potential energy. And the other question was, using the data you obtained in tracker, make 2 separate estimates of the oscillation periods. The first one is estimating the period of oscillation from the X position data, and the second one is estimating the period of oscillation from the Y position data. Then we wanted to compare the 2 estimates and discuss. So first, going to the X position data, we got an oscillation period of 1.56. If you remember from previously, the T equals the period of oscillation. So here I just chose about 4 oscillations, and to compare the two. And the X position is about 0.2 greater than the Y position, and this is because the motion is wider than it is short, so that's why it would take longer to oscillate through the X position. And thank you guys for coming to my TED Talk.